Compounds B and C shown below are unsaturated hydrocarbons containing 9 carbon atoms. Part A. Compound B reacts with chlorine at room temperature, but compound C requires the presence of a halogen carrier. In both reactions, the organic compound reacts with chlorine in a 1:1 molar ratio. Part 1. Draw the structures of the organic product of each reaction. So, firstly, the difference between B and C when they react with chlorine is B can react at room temperature, but C needs a halogen carrier. And that's because of the different functional groups in the two compounds. So B has an alkene group, so a carbon-carbon double bond. And that means when it reacts with chlorine at room temperature, it's going to undergo electrophilic addition. But compound C has this benzene ring, and so it needs a halogen carrier because it's going to undergo electrophilic substitution. So if we draw the products of B and C, so if we draw B first, so most of B is going to remain the same, except this carbon-carbon double bond is going to be replaced with 2 chlorines. Then if we look at C, so what we're doing on compound C is we're substituting one of the hydrogens for a chlorine. So here we can add our chlorine, but the rest of C is staying the same. So you can see what electrophilic addition versus substitution looks like, because addition, you're adding these chlorines, so you don't need a double bond, but with substitution, you're replacing a hydrogen. So to get the 2 marks for this question, you get a mark for each organic product that's correct. Part 2. Explain the relative resistance to chlorination of compound C compared with compound B. So, as discussed in the last part of the question, the difference in the relative resistance to chlorination is due to the double bond versus the benzene ring. So if we break this down into reasoning, or scientific and chemical reasoning, so in B, the electrons, or the pi bond, which is the carbon-carbon double bond, is localized. So the electrons are localized and the pi bond is localized. But in C, the electrons, or the pi ring system, is delocalized. And this is going to mean that B has a higher electron density. So the electrons are very densely packed in this double bond, whereas in the benzene ring, they are more spread out. The electron density is lower. With a higher electron density, that means you're more susceptible to electrophilic attack. So to get the 3 marks for this question, so you get a mark for saying that the B electrons are localized or that the pi bond is localized. Here I've written a slash to indicate you can either say electrons or pi bond. Then you get your 2nd mark from saying in C the electrons are delocalized or the pi ring system is delocalized. So again I've written a slash to show you can write either. Then you get your 3rd mark for saying that in B the electron density is higher and that B is more susceptible to electrophilic attack. But you don't need to say more susceptible to electrophilic attack. They will also accept that B accepts the electrophile more, or B polarizes the electrophile more. And instead of saying the electrophile, you can write chlorine. They will allow that. Part 3. Outline the mechanism for the reaction of compound C with chlorine. Show the role of the halogen carrier. As I said in part 1, this mechanism that we're dealing with compound C is electrophilic substitution, where we substitute one of the hydrogens on the benzene ring with a chlorine. So the key in this question is that we need to show the role of the halogen carrier. So we need to start with how the halogen carrier helps us form an electrophile. So an example of a halogen carrier could be aluminium chloride, so AlCl3. And then we're going to add chlorine and produce a Cl+, that is going to be our electrophile. And then we also produce AlCl4-, which we're going to come back to at the end when we show how the halogen carrier can be reformed. So if we start by drawing compound C as our starting material, and then we're going to show how it initially reacts with the electrophile. So that's going to be Cl+. So what happens is the ring is going to be attracted to this electrophile, and we're going to produce an intermediate. So the mark scheme is pretty picky when it comes to how you draw the intermediate. So this curly arrow needs to be exactly on the points here on the dotted line. So it can't go above the dotted line, and it needs to meet the corners of this hexagon. Then we draw the side products on of the methyl groups, and wherever you want your chlorine to be added, you need to draw your hydrogen that you're going to substitute and then your chlorine. So you can do it anywhere on compound C because you're going to get the same product at the end. But if one of your groups had a directing effect, for example, then you would have to put it on a specific hydrogen or a specific carbon, and a specific hydrogen would be replaced. But because you're going to get the same product here, it doesn't matter where you're going to add your chlorine. Then we're going to draw an arrow of the hydrogen being attracted back into the intermediate so that we can substitute it and produce our product. So we're going to have our benzene ring reformed, our side groups stay the same, and then our chlorine is going to be added with our H+ that's been substituted. Now, this H+ is going to be added to our AlCl4 that we formed at the beginning, and we can reform our halogen carrier, so AlCl3, and then we're left with hydrogen chloride. So this is electrophilic substitution. It's a very common example, and if you did struggle with this question, it's worth maybe having this as an example and then playing around with different compounds and different halogens and halogen carriers, because it's a really good mechanism to have in your back pocket for these exams. To get the 5 marks for this question, you get a mark for generating your electrophile, you get a mark for attacking your Cl+, so the first step of this mechanism, you get a mark for your intermediate, and then you get a mark for the curly arrow coming from the carbon-hydrogen bond and reforming the pi ring. And then you get your 5th and final mark from showing the regeneration of your catalyst, which we've done right at the bottom here. Part B. Compound C can be prepared by trimerization of propanone, using concentrated sulfuric acid as a catalyst. Suggest an equation for this reaction using molecular formulae. So the key bits of this question are that we're preparing compound C through trimerization of propanone, and we need to show the molecular formulae in the equation. We don't need to write sulfuric acid in our equation because it's a catalyst, so we'd write it at the beginning and the end. So it's not changing and it's not going to be relevant in our equation. You could write it over the arrow if you wanted to, but the mark scheme does not require this. So firstly, let's look at propanone. So that's going to be a 3-carbon chain with a ketone group on carbon number 2. So working out its molecular formulae, that's going to be 1, 2, 3 carbons, so C3, and then 6 hydrogens, so H6 and then an oxygen. So the way we've worked out the hydrogens is each carbon must have 4 bonds. So it's got 1 bond going to this other carbon here, but it needs 3 more. So it's got these 3 lines of hydrogen, hydrogen, hydrogen. So then if we look at C, well, we know in the question it's got 9 carbons. So we don't need to worry about counting the number of carbons because we know it's got 9. So C9, but we need to work out how many hydrogens it's got. So again, we've got 3, 3, and 3, so 9 so far. But then we've also got 1, 1, 1, so 3 singular hydrogens. And that's because we've got these alternating double and single bonds in our benzene ring. And that means that you're going to have a group that's going to be able at each. But here we've got a methyl group, here and here. So the remaining gaps are going to be hydrogens. So counting these all, we have H12. So we can begin to construct our equation. We have C3H6O, and that's going to produce C9H12. We're also going to form water as a byproduct. And if you are unsure about why, you can look at propanone and see that it's got this oxygen group. And compound C doesn't have any oxygens. And a very common byproduct when it comes to polymerization is water. So now we need to balance the equation. So we need 9 carbons, so that means we need 3 propanones. And if we multiply by 3, that means we're going to have 3 oxygens, so we need 3 waters. And adding these 2 3s is going to balance out our hydrogens. So to get the 3 marks for this question, so you get a mark for the molecular formulae, you get a mark for having water as a byproduct, and then you get your final mark for balancing the equation. Part C. An organic chemist is investigating compound D for possible use as a medicine. The chemist proposes a synthesis of compound D from compound C. Part 1. Predict the number of peaks in the carbon-13 NMR spectra of compounds C and D. So the key thing in this question is that it's the carbon-13 NMR spectra that we're trying to look at. And whenever you're looking at spectras and you're trying to work out the number of peaks, the first thing you need to do is look at symmetry. So if we start with compound C, we have a line of symmetry here, we have a line of symmetry here, and we have a line of symmetry here. So 3 lines of symmetry. Then if we try and work out the peaks, so we only need to look at one little section here. So it's going to be this little bit of the pie. So we got 1, 2, 3 carbon environments here. And then if we go around the rest of the compound, we have 2, 1, 3, 2, 1, and 3. So you can see there's 3 3s, 3 2s, and 3 1s. So it's going in accordance with our 3 lines of symmetry. So then if we work out and we look at number of peaks, we've got 3, so we can write this in the table. Under compound C, we can put 3. Then if we look at compound D, so if we look at its side group first, we have 1, 2 carbon environments. But then moving on to the benzene ring, we have 3, 4, but we've got 2 4s because we've got this line of symmetry here. So 4, 4, 5, 5, 6, 7, and then we've got 8 and 8 because these 2 methyl groups are going to be the same carbon environment. So we have 8 carbon environments, so 8 peaks for compound D. To get the 2 marks for this question, you get 1 mark for 3 and then 1 mark for 8. Part 2. The chemist develops a 3-stage synthesis of compound D from compound C. Complete the flowchart and show structures for organic compounds. So this question relies heavily on your use of the reaction pathway map. So if you struggled with this question, I would look back at this reaction pathway map and try and learn it, or make a revision resource to try and learn it. So the first bit of this question is that tin and hydrochloric acid are very commonly used to go from a nitro group to an NH2 group, or an amine group. So that means we're going to have to form a nitro group from compound C. So if we draw out what we think the product should be, so we're going to have everything mostly the same, except we've got this NO2 group here, or on any of the 3 carbons. And the reagents for this is you have nitric acid, so HNO3, and then your catalyst is going to be sulfuric acid. So this is another example of electrophilic substitution, which we've covered in a previous bit of this question. But if you wanted more practice, you could use this as your example. So then when you add your tin and your hydrochloric acid, you're going to form your amine. So the NO3 is going to reduce and you're going to form NH2. Then we're trying to go and form this amide. So on your flowchart, the reaction for going from an amine or a primary amine to a secondary amide is when you add an acyl chloride. So that's going to be CH3COCl, because your acyl chloride has to have a CH3 group here, and then your CO and then your Cl would have been here, but you replace it and you form hydrochloric acid. So one of the hydrogens from the NH2 and then your chlorine from the acyl chloride form hydrochloric acid in this reaction. So to get the 5 marks for this question, you get a mark for each of your products, and then you get a mark for your reagent of nitric acid, you get a mark for saying sulfuric acid as your catalyst, and you get a mark for your acyl chloride as your reagent in step 3.